Hi, and welcome back. Let's work on this problem. What wavelength of light is emitted when an electron in a hydrogen atom transitions from n is equal to 5 down to n is equal to 2? Okay, so if you want to pause the video and try to work this out, and now I guess I'm assuming you've unpaused the video. So remember that the energy released, and an energy in a hydrogen atom of this electron. And remember, what we're going to do, you can really only do this in a hydrogen atom, or really you can only do this in an atom which has one electron. It's the only model or the only type of atom that this model works for. But the energy is going to be given by this equation. We could say minus 2.18 times 10 to the minus 18 joules times 1 over the final n level squared minus 1 over the initial n level squared. So that's the equation we're going to use. And so now, pretty much what do we have to do? Well, we just have to plug in our two different numbers, right? And which one? So we have a transition in this height of this electron where it starts at 5, so our initial is going to be 5, and it transitions down to 2. So our final is going to be 2. So let's just go ahead and rewrite that. And actually, while we're doing that, just before we do that, we want to figure out what the wavelength is, right? And we know that the energy of one photon is going to be equal to h times the frequency, h nu. And what is nu equal to? Nu is going to be equal to the speed of light divided by the wavelength. So that should be, so now how would we rewrite this and solve for, and in order to solve for, and remember what we're trying to solve for, we want wavelength. And wavelength is right here in this equation. Wavelength is given by lambda. So now we can say at the end of this equation, so our energy is going to be equal to all of this stuff. So we can say that all of this stuff is going to equal wrote the wrong thing. It's going to be equal to h nu. And nu is going to be equal to this, is going to be equal to c over lambda. So we can rewrite this as h and just replace nu with c over lambda times c over lambda. And lambda is what we're looking for in this equation. So actually I'm going to, hopefully you don't mind, I'm just going to erase this stuff down here, give myself a little bit more room. One sec. Okay, there we go. So now we've got everything we need, and I can start plugging in some numbers. Let's do, though, what I want to do right now is I just want to do a little bit of algebra so we can figure out maybe a little bit more general form when we want to just plug this into the calculator and get an answer. So actually, you know what? Everything in here, all of this stuff, let's actually just call this A for a second, just because I want to do a little bit of algebra to work this all out and show you what exactly we're going to be looking for. So we say that A is going to be equal to h, which is h is Planck's constant, times c over lambda. Okay? And we want to solve for lambda. So the first thing we do is we divide both sides by h and c. So we get a over hc is equal to 1 over lambda. And then what do? We just have to invert, right? We just have to flip both sides. So then our final answer, lambda, is going to be equal to Planck's constant h times the speed of light c all of that divided by, and remember we just called A all of this stuff that's in there. So our final answer, what we're going to, I guess, start plugging in is we're going to say that lambda, our wavelength, is going to be equal to Planck's constant times the speed of light c divided by A, divided by all of this stuff. Hopefully I'm not confusing you. I am going a little bit faster because, we are doing this. Hopefully this is review from earlier on in the playlist. So actually, you know what? I am going to erase the rest of this stuff. I'm going to start erasing this. Okay. Sorry. It takes me. You know what? I am going to. There we go. Increase my brush size. Okay. So now we've got our generalized form for how we're going to get wavelength out of this. So let's actually just start plugging in some actual numbers. So we can say lambda, which is what we're looking for, is going to be equal to Planck's constant h, which remember is 6.626 times 10 to the minus 34. Now I'm going to leave the units off of that for right now. Times the speed of light c. So times 3.00 times 10 to the 8th. And now we just have to divide all of this. We're just going to divide all of this by all of this stuff that's in here, by what we called A. So we're going to divide everything by minus 2.18 times 10 to the minus 18 times 1 over some numbers here. So 1 over n final squared. So we know n final is 2, so what's 2 squared? Well, that's going to be 1 over 4, right? And then 1 over n initial squared. N initial is 5. So n initial squared, what's 5 squared, is going to be 1 over 25. So that's pretty much it. And actually, you know what? I'm going to, hopefully we don't need this anymore. I should have planned my space a little bit better. Hopefully you don't mind. I'm just going to erase that real quick. Okay, so now we could just start plugging this into the calculator right now. Actually, what I'm going to do, just because I like to deal with everything with scientific notation at the end, is I'm just going to do a little bit to move some of our scientific notation out of this expression. So the first thing we could say is we could say that this is going to be equal to, and we could say that, so if we move this times 10 to the minus 18 to the top of our fraction, we can just say that that's the same thing as if we multiplied, the dividing by 10 to the minus 18 is the same thing as multiplying by 10 to the positive 18, right? So we can actually, let's just start rewriting some of this. So we have 6.626 times 3.00, all of that divided by minus 2.18 times this fraction that we've got, 1 over 4 minus 1 over 25. And then all of that, I'm just going to move over a little bit. So we've got, we've got positive 18 and positive 8. So what's 18 plus, so we've got 18 plus 8. That would give us 26, right? So we've got 26 minus 34. So that would give us times 10. So the final scientific notation, after we do all of this other computation, the final scientific notation, and all I'm doing is I'm adding these exponents, except, we said that this minus 18, when we multiply by it, it's going to become positive. So we take 18 plus 8 gives us 26, and then 26 minus 34 is going to give us minus 8. So that's where I got all of that. Hopefully not too confusing, and hopefully you don't mind me going through this kind of quickly. Now we're at the point where we can just really start throwing this into the calculator. So I'm going to go ahead and get the calculator up. And the very first thing I'm going to do, just because this calculator isn't good with handling these fractions, is I'm going to just work out what this fraction, what this would be, this 1/4 minus 1/25, so we can actually just get a decimal number to put in there. So I'm going to say 0.25 minus, I'll just do my parentheses, 1 divided by 25, close parentheses, 0.21. Okay. So this whole thing right here, this part, is going to be 0.21. So now we've got everything exactly like we would need it to just throw it all into the calculator. So we start off with 6.626 times 3 divide by 2.18 divided by 0.21. And remember, this is going to be negative, right? So we say that this is going to be negative 43 point, and how many, well, we're going to say that this is negative 43.42 for right now. So this is negative, one sec, this is, okay, it's out to, there it goes, negative 43.42 times 10 to the minus 8, and we're looking for wavelength, so wavelength is going to be measured in meters. And so now we just want to move this decimal place over one unit to, we could actually do this, we do this either way. Maybe we wanted to give this expression in nanometers. And what would this be in nanometers? Well, we would just move this decimal point 1 over. If we wanted to give this in nanometers, nanometers is some expression times 10 to the minus 9, right? So what would we do if we wanted to give this in nanometers? We would just move this decimal place over one space to the right. So we would say that this is equal to, and we actually don't having a negative length, I guess doesn't make any sense for right now, but so we would say that this, so our length, if we wanted to give it in nanometers, would be 434 nanometers. Or another way of saying that, if we wanted to just give this in straight scientific notation, we could also say, one sec, computer's freezing on me, there we go. If we just wanted to give this in straight scientific notation, we could also just say that this is going to be equal to 4.34 times 10 to the minus 7 meters. So those are our answers. I guess probably you would be better off giving the answer in scientific notation, sort of like always. But there might be, if you're taking the test and there's an answer bank, you might have to choose the correct answer in nanometers rather than in meters. So it's good to know how to, if you needed to give this in nanometers, that nanometers would be the same thing as saying some number times 10 to the minus 9. And if you wanted to get 10 to the minus 9, you just move the decimal place 1 over to the right. So hopefully that wasn't too confusing, and hopefully you didn't mind me going through this kind of quickly. So anyway, thanks for watching, and I'm just going to keep on doing review problems. See you soon.